In VCE Algorithmics, we are going to learn to use telescoping to solve a recurrence relation. So there are two kinds of recurrence relations we solve, each relating to recursive algorithm design. The first is decrease and conquer, and that's where we reduce the problem size by a constant amount every time we call the algorithm. For VCE Algorithmics, we always perform some constant time operation outside the algorithm. For other algorithms, it might not be constant time. Now, let's consider the following algorithm. Pause the video, read it a couple of times to see how it works. Now, one thing to note, just as an incidental thing, having taught this for a while, we're not using Python list indices here, okay? No. We want to make sure that we're writing the pseudocode in a way that everyone can understand. Well, of course, in an exam, you've probably been given this to analyze. Just worth making that point now. So, every time we do this algorithm, calling it on a list of n items long, we reduce the problem space by 1. We also carry out 4 operations each time. Now, whether it's exactly 4 doesn't entirely matter. The important thing is that it's linear, but we're going to go through this as accurately as we can. So we can represent this as t of n equals t of n minus 1 plus 4. So that means the time it takes to solve a problem of size n is whatever it takes to solve a problem of size n minus 1 plus 4 operations. And this recurs down n minus 1, n minus 2, n minus 3, etc. until we get to our base case. Our base case is t of 0 equals 1. It's t of 0 because the problem size equals 0 when our base case is called. So that's lines 1 and 2 inside the algorithm. We're going to solve this by doing a lovely technique called telescoping. So consider the first few and the last few lines of how this is going to look. Okay, hopefully that all makes sense. We're going to rewrite it by subtracting all of the t of n minus 1, n minus 2, etc. to the left-hand side of each equation. And now if we add all of these lines together like some giant infinite simultaneous equation, what we're left with on the left-hand side is t of n minus t of 0. What we're left with on the right-hand side is 4, and we've got that n times. You can count the lines on the left-hand side. It goes from 1 to n. So on the right-hand side, we must have 4 times n. That's why that base case matters. If the base case was t equals 1, our base case, we would be calling this n minus 1 times. Now we know that t of 0 equals 1. That's what so when we call the base case, we're saying that just takes one line. We solve that and we get t of n equals 4n minus 1. Now we've hopefully seen the video on big N notation. We know that this is linear, so we refer to this as big O of n. Now in VCE Algorithmics, we're only required to solve things of this form, where the decrease and conquer algorithm is t of n minus a plus b, where a and b are both constants. And the base case is also going to be a constant. We know it's always going to come out as big O of n, but we must show the process. And that's what we're going to practice a few more times in this video. So let's consider another algorithm. Again, pause and have a go at writing down what is the recurrence relation going to look like. Well, what does it do first? Hopefully the name makes it fairly obvious. You can see how it compares the first 2 items in a list to see if they're equal, adds this to a total, and then reduces the problem by 2. We ignore the last item if there's an odd number of items, so in that sense you could say it's not a perfect algorithm. Our recurrence relation then is t of n equals t of n minus 2 plus 1, since there's one operation outside the recursion. Now the telescoping analysis we'll do once again. In this case we have to consider 2 base cases. So we're going to first consider what happens when there's an even number of items. So we can imagine we're going to go 0, 2, 4, 6, 8, all the way up to whatever even number it is. So this part is going to look the same for both of them, except the last line is t of 2 equals t of 0 plus 1. We subtract all the terms again, and then we work out how many times does this run when we telescope all the parts together. It's going to be n minus 2 times. The safest thing to do is try some examples on your fingers. So let's say n equals 10. We're going to go 2, 4, 6, 8, 10. Well, that was 5 times. So we can see it's n over 2. So we can say t of n equals n over 2 plus 1 because t of 0 equals 1. And of course that gives us big O of n. Now let's see how this works for an odd thing. It's all very similar, except that last line is now t of 3 equals t of 1 plus 1. We move everything over. This time, when we telescope it, it's going to run n minus 1 over 2 times. So let's pick an odd number, let's say 11. So that is going to go 3, 5, 7, 9, 11. So that's 5 times. So we're going to take away 1 and divide by 2. That's not perfect mathematics, but it works. And then everything else is very, very similar. We end up with, of course, another linear expression. So we have big O of n. Here are two for you to try yourselves. Make sure you pause the video and give it a go. The first part I think is usually quite straightforward. We write out some terms, we subtract them all from both sides. This one, you've got to be slightly careful. I mentioned the base case matters. So if we have n items, this only runs n minus 1 times because the base case is 1, so we're starting on 2. So we have t of n minus t of 1 equals 5 bracket n minus 1. And we do some basic maths. We get 5n minus 2, which gives us big O of n, obviously. The next one is pretty fiddly. We know that this part is going to be the same, but we've got 3 different cases we need to deal with, 3 base cases where we have t equals 3, 2, or 1. So first we'll consider, and this is working on multiples of 3. So if we have, let's say, 3, 6, or 9, then our base case is going to be 3. So that's what's happening over here. This is going to be 2, 5, 8. So that's all multiples of 3 minus 1. And this one is going to be 1, 4, 7. So that's multiples of 3 minus 2, or multiples of 3 plus 1, depending on how you want to think about it. Now, this next part of counting the lines is quite tricky. For the one on the left, you can see we've got n divided by 3 minus 1 times. So let's say n equals 9. We know that is going to go, well, it would be 3, 6, 9, but we don't run the 3 because that's the base case. So it's just 6 and then 9. So hopefully we can get a feel that we're going to divide it by 3 and then subtract 1. For the next one, where we have, let's say n equals 9 for the next one. Well, sorry, not n equals 9. We'd say n equals, 11. So 2, 5, 8, 11. So that is going to run 5, 8, 11 times. So 3 times. 11 needs to run 3 times. I look at this as saying, well, we're going to add 1 to bring it up to 12, divide it by 3, and then subtract 1. You could equally have written it as n minus 2 over 3, and obviously that cancels out to the same thing. The last one, 1, 4, 7, 10, etc. Struggling there. Let's take n equals 10. That's going to go 4, 7, 10, so 3 times. So in this case, I've gone the other way. It doesn't really matter. I've gone n minus 1 and then divide that by 3. Okay. So in each of these cases, those 3 bits in blue tell you how many times you're going to have a 5 operation thing happening on the right-hand side. So let's consider all of these 3, and I'm just going to simplify that middle one to make it a bit more consistent and make the algebra a bit simpler. And for each of these, I'll just step through it. I'm not going to read out the steps. We would end up with this for the first one, this for the second one, and this for the third one. All of that is simple year 8 maths, hopefully. We can all make mistakes when we're tired. And all of these lead to big O of n, just as we thought they would. So hopefully that is everything you need for this, for telescoping in algorithmics. If you want to try something a little bit harder, especially if you watched my video on summation, this one is actually fairly achievable. So in this case, we are performing n operations outside each recursive call. Give this a go. You don't have to, but aim high. we write out our telescoping things. Note that the right-hand term goes down, so it's n, n minus 1, n minus 2, etc. So everything else is the same. We shift all that over, and now we are adding all those terms on the right-hand side. 1 plus 2 plus 3, blah, 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 n minus 1 plus n. Now, what do all those numbers equal? Hopefully you are aware that is the sum of all the natural numbers. So the right-hand side is the sum of all the natural numbers, which if you've been doing maths for long enough, you'll have noticed this comes up, is n bracket n plus 1 divided by 2, which makes this all very easy. If you happen to know that, we have t of n minus t of 0 equals that. T of 0 equals 0, so we just end up with this, which gives us big O of n squared. Now, we could quite easily have casually got to big O of n squared as well, because we know that all those constants on the right-hand side, the minus 1, minus 2, etc., don't really make any difference. We've got n lines, each of them with an n in them, so it's going to be n squared. But this is a slightly more precise and elegant way of working it out. Any questions? Pop them in the comments.